Welcome to AI Peer Review. Today we're diving deep into a really interesting paper that's trying to push computer vision forward.
Oh, yeah. What's the focus?
It's about extending image segmentation, identifying objects in pictures, to the much trickier world of video.
Video segmentation.
That
Always a challenge.
Exactly. The paper introduces SAM2. It builds on the segment anything model, SAM, which was already pretty impressive.
Right. SAM made waves for image segmentation. So SAM2 is for segment anything in videos.
That's the goal. And it's a pretty ambitious one.
It really is. Segmenting in images is one thing, but adding that time dimension, motion,
Yeah.
it changes the game entirely.
For sure. Think about AR, VR, advanced robotics, self-driving cars.
They all need to understand moving objects, segment them accurately, track them. It's fundamental.
And the paper points out, rightly I think, that current methods often struggle.
Yeah, the usual approach is kind of bolted together, isn't it? You take an image segmenter like SAM.
Right, and you combine it with a separate video tracker.
Exactly. And those hybrid systems, well, they can be brittle. They don't always handle the huge variety of objects you see in the real world.
And interactive refinement, trying to fix errors on the fly.
Often clunky. Or just not very effective. You sort of lose that unified control.
Yeah, there's been this gap, right? Needing a single model that gets both the spatial part, the segmentation, and the temporal part, the consistency over time.
And crucially, one that lets you interact easily. Tell it, no, this is the object I care about across the whole video.
Okay, so let's unpack SAM2 itself. What's the core idea that lets it handle video directly?
The key innovation seems to be this integrated memory mechanism.
Memory. So it remembers the object.
Sort of, yeah. It maintains awareness of the object you've prompted it with over time, frame to frame.
Ah, so it uses that memory to predict where the object will be in the next frame.
And to refine the segmentation. It
Mhm.
looks back at what it saw, combines it with the current frame, and any new prompts you give it. It develops a persistent understanding.
That sounds much more integrated. How does that work architecturally? They mention a streaming approach.
Yes, it's designed to process video frame by frame, like a stream. The heart of it is this memory attention module.
Memory attention, okay.
This module basically conditions the processing of the current frame based on information stored in a memory bank.
And what's in the memory bank?
Information about the object from previous frames, both frames you clicked on, and maybe recent frames it processed automatically.
So it's constantly looking back.
Exactly. And what's neat is, if you feed it a still image, the memory bank is just empty.
Ah, so it naturally degrades back to acting like the original SAM.
Pretty much. It's designed as a genuine generalization, handling both images and video within the same core framework.
That's clever. But to train something like this, you need a ton of video data, right? Properly annotated.
Absolutely. And that's the other major piece of this work, the SAV dataset they created.
SAV. Okay, what's special about it?
Well, they argue existing video datasets just weren't cutting it. Not enough scale, not enough diversity.
What kind of diversity were they missing?
Often focused on whole objects, specific categories like people or cars.
Yeah.
And critically, not enough annotation of object parts. If you want to segment anything, you need data that reflects anything.
Makes sense. So how big is SAV compared to, say, Davis or YouTube VOS? I remember the intro mentioned some big numbers.
The numbers are pretty staggering. Table 3 in the paper lays it out. SAV has about 51,000 video.
Okay, that's a lot of videos.
But the key is the number of annotated segments, or masklets as they call them, over 640,000.
Wow.
Yeah. They claim it's 53 times more annotated masks than the next largest VOS dataset. Even discounting the automatic annotations, it's still 15 times bigger.
So datasets like Davis, YouTube VOS, UVO Dense, VOST, Burst MOS, they're just much smaller in terms of total annotations.
Significantly smaller, yeah.
Yeah.
That scale difference is likely a huge factor in training a more general model.
And what about the type of content in SAV? Is it just more the same or genuinely diverse?
They aim for real-world diversity. It's about half indoor, half outdoor scenes, average video length around 14 seconds.
Okay.
And importantly, the videos come from 47 different countries. Figure 10b shows the map. It's pretty global.
So less biased towards specific environments or regions.
Hopefully. And they also annotated object parts extensively, not just whole objects. Figure 4 gives some visual examples of the masklets, both manual and automatic ones. You see that granularity?
Right. Let's dig into the SAM2 architecture more. We mentioned the streaming approach and memory attention. What are the building blocks?
Okay, so first, there's the image encoder. For each frame, they use a pre-trained Hyera encoder.
Hyera, based on MAE, masked autoencoders.
That's right. It extracts features from the frame, Crucially, it's hierarchical.
Meaning it provides features at different scales.
Exactly. And that's important later for the decoder to get fine details right. This encoder only runs once per interaction, which helps with efficiency.
Okay, so you get these hierarchical image features, then they go to the memory attention module.
Correct. That's really the core engine for the video part. It's made of transformer
The
blocks.
standard transformers.
Yep. Using self-attention on the current frame's features, and then cross-attention to the memory bank.
So it's attending between the current frame and the memory?
Precisely. It integrates that past knowledge. The memory bank holds features from recent frames and also from frames where you provided a prompt, like a click.
And how are those memory features created and stored?
There's a memory encoder. It takes the mask predicted for the frame, shrinks it down, and fuses it with the features from the image encoder. Then that goes through a few simple convey layers and gets stored.
They mentioned FIFO queues. First in, first out.
One queue for recent unprompted frame memories and another for the prompted frame memories. It keeps a rolling window of past context.
You also mentioned object pointers earlier. What are those?
Right. These are interesting. They're lightweight vectors, basically derived from the mask decoder's output tokens.
So not spatial features, but like semantic embeddings.
Kind of, yeah. They carry condensed info about what the object is. The memory attention also cross-attends to these pointers.
So it helps the model track the specific object's identity, not just blobs of pixels that look similar.
That seems to be the idea. Helps maintain consistency, especially if the object changes appearance. They also add temporal position info to the recent frame memories to capture motion better.
Got it. And the mask decoder, is it just like the original SAMs?
Largely similar, but with some key additions for video and detail.
Okay.
It gets skip connections directly from the hierarchical image encoder. You can see this in Figure 8.
Bypassing the memory attention. Why?
To give it direct access to those high-resolution features from the encoder helps get really sharp, accurate mask boundaries.
Makes sense. Anything else new in the decoder?
Yes, an occlusion prediction head. It tries to figure out if the object is hidden or partially out of frame.
And what does it do with that information?
If it predicts occlusion, it puts a special learned occlusion embedding into the memory bank for that frame instead of the usual memory feature.
Clever. Sort of tells the model, don't trust the visual input too much for this object right now?
Exactly. And the mask token itself serves as that object pointer we talked about.
Yeah.
Like SAM, it can also output multiple masks if things are ambiguous.
And it picks the best one based on IOU if the user doesn't give more prompts.
Right. Handles ambiguity that way.
Okay, let's switch back to the SIV dataset for a moment. Creating that massive dataset must have been a huge effort. How did they actually do the annotation?
They used a pretty sophisticated multi-stage process they call a data engine.
Data engine. Sounds fancy.
It involved humans working with SAM2, plus an automated pipeline.
So humans use the tool to make the annotations.
Yeah, in the first phase, human annotators used SAM2 interactively to segment parts and instances, made things faster. Then, crucially, a separate team verified every annotation.
Quality control.
Exactly. If it wasn't good enough, it went back for refinement.
You mentioned an automated part, too.
Right. To boost diversity and find where the model fails, they automatically generated mask proposals. By feeding SAM2 a dense grid of points on the first frame of many videos, get lots of potential object masks that way.
And those also went through human verification.
Yep. The good ones were added to SAV, massively increasing the data.
And the bad ones. The ones the model got wrong.
But this is clever. They sampled those unsatisfactory automatic masks and specifically gave them to human annotators to fix, again using SAM2. That was phase 3.
So they used the model's failures to guide the human annotation effort towards the hard cases.
Exactly. Figure 9 shows how this hybrid approach really increased the diversity of annotations compared to just manual work. It's a smart way to get scale and cover tricky scenarios.
That is a really neat feedback loop. Okay, let's get to the results. Does SAM2 actually perform well on video segmentation tasks?
Section 6.1 covers the promptable video segmentation results. They tested it offline.
Meaning multiple passes allowed for error correction.
Right, and also online, so single-pass processing. They did this on 9 zero-shot video datasets, simulating user interaction with about 3 clicks per frame.
And how did it compare to the standard approach, like SAM plus a separate tracker?
Significantly better, according to their results. Table 4 and Figure 14 show comparisons against SAM paired with strong trackers like XMM+, Plus, and Qt.
And SAM2 outperformed them?
On the majority of the 17 datasets they tested, yes. Across different prompt types in a semi-supervised VOS setting, it really suggests the unified architecture has advantages.
That's compelling evidence for the integrated approach. The paper also has a lot of ablation studies, right? Testing specific design
Oh
choices.
yeah, very thorough. The data mix ablation in Table 7 is really telling.
What did that show?
It basically proved the value of their SAV dataset. Training only on older VOS datasets gave much weaker results on the zero-shot benchmarks.
But adding SAV boosted performance.
Massively. Over 12% average improvement just by adding SAV.
Wow.
Combining SAV with the big image dataset SA1B was even better. And the best results came from mixing everything, SAV, SA1B, and the older VOS datasets.
So data scale and diversity are absolutely key here.
Undeniably. It really drives home that point.
Any other standout ablation results?
The data quantity ablation in Figure 6 is interesting. They show a pretty clear power law relationship.
Meaning more SAV data leads to predictably better accuracy.
Seems so. It suggests that if they can scale SAV even further, performance would likely keep improving along that curve.
That's encouraging for future work. What about data quality? Did they look at that?
They did in Table 8. They tried filtering the data based on how much human editing was needed.
Thinking maybe the less edited, easier data was better.
They found you could get strong results with less data by filtering like that, but ultimately, using the full manual SAV set gave the best performance. Quality and comprehensiveness matter.
Okay, and drilling down into the model itself, how did things like resolution or memory size affect results?
Table 9 covers those capacity ablations. Higher input resolution helped, as did training on longer video sequences.
Makes sense. More context.
Choosing the image encoder size higher tiny up to large showed the expected speed versus accuracy trade-off.
And the memory. How many pass frames were optimal?
They found using 6 pass frames in the memory was a good balance.
What about the attention mechanism details, like positional encoding?
Table 10 looked at that. Using 2D ROP, rotary positional embeddings, in the memory attention worked well. And importantly, it allowed them to use flash attention too.
Which speeds things up considerably, especially at high resolution.
Exactly. A nice practical benefit.
And the memory architecture itself, did they try alternatives?
Table 11 shows some comparisons. Storing the memory features directly was just as good as using something more complex like a GRU.
Simpler is better if it works.
Right. And critically, that cross-attention to the object pointers we discussed, that gave a significant boost, especially on the harder benchmarks like LVOS v2.
So those semantic pointers really are important for robust tracking.
Seems that way. It helps the model lock onto the specific object.
It's really cool seeing how all these pieces fit together. The paper also frames this work within a broader concept. Promptable visual segmentation, or PVS. What's the idea there?
Figure 7 illustrates this. They propose PVS as a kind of umbrella task.
Encompassing both image and video segmentation.
Yeah. The argument is that segmenting anything in images, like SAM, and semi-supervised video object segmentation are just specific instances of this general PVS idea.
Where the defining characteristic is interactive prompting.
Exactly. Any visual segmentation where you can guide the model with prompts, whether on one frame or across many, SAM2, by handling both image and video prompts seamlessly, is a big step towards that unified vision.
Okay, so wrapping this up, what are the main takeaways from this deep dive into SAM2?
Well, first, it's a significant advance. We're moving from segmenting anything in a static picture to doing it in dynamic video, interactively. That's a big deal practically.
And the SAV dataset is a huge contribution in itself.
Absolutely critical. It gives the community a much better resource for training and testing these kinds of models.
Yeah.
That data engine they used to build it, combining automated generation and human verification, that's a valuable lesson in how to create these massive data sets efficiently.
The ablation studies also give a lot of insight.
For sure. They really map out how architecture and data choices impact performance. That power law finding with data quantity is especially interesting, suggests there's more performance to be gained just by scaling up data.
It really pushes towards this idea of a general-purpose visual segmentation system.
It does. It makes you think about what a unified visual understanding across images and video really looks like for AI.
Yeah,
And the interactive aspect opens up so many possibilities for applications.
definitely. For anyone listening who wants to dig deeper, the demo and code are available online. The paper links them sam2.metademolab.com and the usual GitHub repo from Facebook Research.
Yeah, worth checking out the demo to see it in action.
It really makes you wonder what new applications become possible when you can segment anything in video this flexibly with memory and interaction. Feels like a really exciting area for innovation.